Sir, what is that you write? N slash M?
Yeah, Newton per meter.
So that's
Oh,
4 newtons per meter, sir.
Yeah. All right, so the last time we were talking about differential equations, and like I said, the course is just taking the maths that you have been learning and modeling it to different situations. So for example, now, let us say that we have a system that it is, you have a spring. Now, they tell you from back in the day that Hooke's law says that force is directly proportional to extension. So if you have a spring, then the relationship between force and extension is F equal kx. If you have viscous friction in a medium, then the usual viscous friction just has to do with if an object is moving through a fluid, and a fluid is any liquid, solid, liquid, or gas that flows or takes the shape of the container over time. Yes, there are gases that are solids that are regarded as fluids. So is any solid, liquid, or gas that takes that flows. So if a car moving through air is going to experience some viscous friction. If you have something in underwater that is rising, it's going to experience friction. So once you're in the Earth's environment and you're moving through Earth's environment, you're going to experience friction. And this frictional force, let me put FV, is K times the velocity. Some constant times the velocity. Let me distinguish between these two K's. So, because if you have, for example, if you're in a car, the faster you move, the greater the force. Let's say you're holding your hand out the window. The faster you move, the greater the force that is pushing back on your hand. So we use the concept of the spring and the concept of friction whenever we are modeling any mechanical system. And so we just want to use this example that we have here. So let us say that
Sir,
yes,
what is that on the thing there? Is that an R or the top?
where? Here?
The thing on the top, yeah.
Here?
Yes, sir.
X. So I'm just going to describe the problem to you now. So let us say that we have mass, and I'm putting as 2 kilograms. So the mass is 2 kilograms and is displaced by a force, and these are the two things that are holding it. So let us say that this is a wall. So the viscous friction is 2 Newton meter per second, and the force due to the spring constant is, so this here that I'm talking about, let me just make it clear. This is my B, my K1, sorry. And this is my K2. So we're just describing the situation and because we're just talking about differential equations in general, but we just want to illustrate or explain that there are many mechanical situations that cause differential equations to arise. So if we take this system that we have here and we look at the forces on it, so if we redraw the whole entire thing, you have the force forward and then the force due to the spring and the force due to the viscous friction, and the mass is m. Now, Newton's law, let me just put in back the displacement, which is x. So Newton's law says no. Well, that shouldn't say Newton's law. Let me use common sense. Common sense. Sorry, I'm having a little problem with the pen here. Don't know why. Okay. Let's use common sense. So the force here is 10, and this is 4, and this is 5. What's the net force?
1, sir.
One.
What is it?
Newton.
1.0,
Newton.
sir.
1.
1.0.
Because you're going to say
1.0.
10 minus 4 plus 5. So the forward minus the backward, give me the net. So the net force is going to be equal to F, in my case, minus FV minus Fx. So let me just write down Newton's law. Force is equal to mass times acceleration. So now, my net force is going to be F minus B times V minus K times X. And that is going to be my net force. The forward minus the back. But we said that net force is equal to mass times acceleration. So mass times acceleration is going to be equal to F minus BV minus KX. If we carry everything over and leave our force, so we're going to have MA plus BV plus KX is equal to F. Now, we say that speed is rate of change of displacement, and acceleration is rate of change of velocity. So if we're going to, if we are going to differentiate velocity, which we have here, velocity, which is dx dt, then if we're going to differentiate that, then we can write it as d2x by dt squared. So if we put all of that together, we are going to get that m times d2x by dt squared plus b times dx by dt plus kx is equal to f. We can put in numbers. This was 2. This was 2. is 4 and this is 10. So this is my differential equation, which goes to set dx d2x if I divide through by 2. So now, we can assume our initial conditions to be 0.
So it shouldn't that be 2x?
And again,
Shouldn't that be 2x equal 5?
yeah. So if we assume the initial conditions to be 0, so that we are saying that the block was not moving at the start. Then what we're saying is that t equals 0, then x would be, it was at the starting point and the velocity was 0. So now we have a set of equations that we can solve for our system. So let us proceed to
Sir, A that, sir?
wait, this here, so
No, the A equals 0. This other T equals 0.
x.
Or X, all right.
We're saying that it was at the starting point. We're assuming that it was at the starting point and it was moving. So the speed is 0 and the displacement is 0. So we're making those assumptions in the absence of any information. So remember what we said, the first thing you have to do is you have to solve a homogeneous equation. So what do we do to solve the homogeneous equation? Remember now, homogeneous equation means that this thing here is equal to 0. So that's the equation we're going to solve first. So what are we going to write?
The auxiliary
The auxiliary equation.
All right, so what the auxiliary equation? What do you call that?
so it's going to be 1k squared plus 1k plus 2.
All right. Last class with me racking my brain. Next class we're going to be using MATLAB to solve our equation. All right. So we're going to use b squared plus 1 squared minus 4 times a, which is 1, times c, which is 2, all over 2 times 1. So that is going to give me minus 1 plus or minus 1 minus 8 is 7. There's root 7j. I remember that we said minus 7. Last class we said minus 7 is minus greater minus 1 times. This is equal to j. And we
Divided by 2.
divided by. So now, so this is k. So therefore, how did we say right now this equation now? x is equal to the real part. Let me write it like this, minus a half plus or minus root 7j over. So what did we write as our, would we write as our solution? If that the roots of our equation are complex.
E
So e to the minus 1/2 open bracket m cos square root of 7j over 2 t plus n sine square root of 7j over 2 t close bracket.
We got the j.
yeah, J for the same side, yeah.
Oh, you vote the j's?
Yeah.
Oh,
The side of the same. Yeah.
All right, so is the real part is the exponential function, and the part of the j is the trigonometric function. All right. So now, so at t equals 0, x is equal to 0. So we can plug in 0 in for t and x and see what we get. So we get 0 is equal to e to the minus a half times 0. M cos root 7 over 2 times 0 plus n sine root 7 over 2 times 0. This anything raised to power 0 is 1, cos of 0 is 1, so therefore we get that m is equal to 0. 0 is 1. So therefore now we are left with x is equal to e to the minus a half t, and then we put the n first, sine root 7 over 2t. So let's differentiate. Dx by dt is equal to, put on the first, n e to the minus a half t. Differentiate the second, so sine. When you differentiate the second, you get, so put on the first, differentiate the second, root 7 over 2 cos root 7 over 2t plus put on the second, which is sine, and differentiate the first. So we're going to get minus, when you differentiate an exponential function, what is in front of t comes in front, so that's minus a half e to the minus a half t. So we say that at t equals 0, ex by dt equals 0. So therefore, we're going to plug in, for all of them, we're going to plug in 0 everywhere we see dx by dt and we see t. So it's going to give me 0 is equal to n e to the minus half 0 root times root 7 over 2 cos root 7 over 2 times 0 minus a half e to the minus a half 0 sine root 7 over 2 times 0. So 0 is equal to, the raised to the power of 0 is 1, so that's n is 1 times root 7 over 2. Cos of 0 is 1 times 1 minus a half times 1 sine of 0 is 0. So we're going to get 0 is equal to an issue. No, I shouldn't. Anyway, and then we'll just solve the issue then. 1 times 1 is 1 times 7 over 7 root 7 over 2 minus. We have to adjust our initial conditions because our initial conditions, I am going to was still in the start. So I'm going to just let the x by dt that it is moving at a speed of 1. So as not to trivialize solution. Sorry about that. So this is supposed to be 1, 1, 1. What is it? All right, so carry across is 2, carry across is 7. So we're going to get n is equal to 2 over 7. So therefore, our x is going to be equal to.
You just said something about changing dx by dt.
Yeah, changing the initial condition. So as not to trivialize the solution. So the speed is 1 at the time. I just change. So dx dt.
Why, sir?
Make it equal to 1. No, because I didn't. If I let it be equal to 0, we're going to trivialize the solution. So basically, it's not the solving of the differential equation that I want to get at. Is some instead of complicating up and talking about is that a trivial solution. I just wanted to just make it equal to 1. Because I want us to just focus on the actual this part up here more than this part down here. But all right, so I just change.
All right.
I just change it to 1. All right. So this is going to give me x is equal to n, which is 2 over 7 e to the minus half t sine root 7 over t. And so this would be my solution. So if you want a picture of the motion in it's an exponential sine graph. So it's going to be going back and forth. The e to the minus a half is the rate of decay, and inside it's going to be sine root 7 over t.
So,
The
sir,
amplitude of the function.
why I never do the second differential one, sir?
Oh, never do that yet.
Oh, sir, let's stop at the first.
Right, so this is the homogeneous solution. So never do that yet. All right. So just bear with me a little bit. So our solution is going to be that. I just wanted to point out that the amplitude, the maximum value, would be the 2 root 7. And it will decay at that with time. So that is the solution for the homogeneous equation. But our thing is not equal to 0, because when we solve it is equal to 0.
So could you clarify what you just said, sir? The E
This is
over
equal to-
E is the rate of decay and the sign is the amplitude?
No. The E is the rate of decay, the 2 over 7 is the amplitude, and the sign just tells you, well, basically the same root 2 here gives you the frequency at which it oscillates. And you know that it is following a sinusoidal form, but it is sinusoidal. E to the negative half means that it is decay. So it is going back and forth. And will eventually stop.
Thank you, sir.
All right. So now, the plus 5. So this thing is not equal to 0, as we have said. It is equal to 5. So let me write it back down there. So we have to find what is called a particular integral. And what we said, that the parents spit out the baby. So the baby must look like the parents. So we're going to try to make sure that we include the grandfather. So we're going to put 5t, sorry, a linear function, a t plus b. Meaning to say, I took this thing and differentiated again, and I get 5. So I must have differentiated at most a linear function to get the 5 out of. All right, so I'm going to try a linear function. So dx by dt is going to be equal to a, and when I differentiate it twice, I'm going to get 0. So I'm going to plug that in. So I'm going to get 0 plus a plus 2 at plus b is equal to 5. So this is going to be 2 at plus a plus 2b equal 5. So now, if you compare coefficients, there's t over this side, but there's no t over that side. So therefore, 2a, the coefficient of t, must be equal to 0 because there's no t over the right-hand side. So that means that a equals 0. And then now, if a equals 0, that's 0 plus 2b is equal to 5. So therefore, b would be equal to 5 over 2. So my particular integral is 5 over 2. So my general solution to this whole equation now is going to be X is equal to, forget what this was, 2 over root 7 e to the minus a half t sine root 7 over 2t plus the particular integral, so it's plus 5 over 2. So this would be the total solution for the equation. Right, any questions?
No, sir.
No, sir.
So, we just do all of this to find the integral and the particle integral equation.
Well, we do particle. Well, the particle integral is just the last part. The first part is the solving of the homogeneous equation.
And okay. It's okay, go back down to the last part, repeat, sir. Okay, thank you, sir.
So now,
You can continue, now, sir. You can continue.
I didn't hear.
I say you can continue, sir.
Okay. Okay. All right. So let me look at another problem. Find it okay. Yeah, just finding the problem. A second there. All right. This thing doesn't- So shows an aircraft wing attached to a jet plane. Modeled as shown. Coefficient of friction counted. So in other words, the plane wing is going to be modeled and it's going to be looking at the vibration. So it's attached as going to be looked at in terms of this is a simplistic diagram, but you have to start somewhere. So the force is on the wing is UT. So the wing is prone to vibrate up and down. The mass of the wing is M, and as it vibrates, it's going to it's attached. So therefore, the K for the spring constant is going to take into consideration that the wing is attached, so it is going, when it's vibrating, it's going to act as if it is attached to a spring. And as the wing goes through the air and vibrates through the air, it's going to encounter this viscosity. So this model over on my right is supposed to be a diagram for the wing of the aircraft, or a model for the wing of the aircraft. All right, so this is K is the stiffness of the wing, B is the friction that it encounters, M is the mass of the wing, and U is the force on the wing. And X is the displacement of the wing. So now, so if we are to model a differential equation off of that. So sorry. Sorry, this thing that. So you have to get drinking to draw my very bad diagram. So whoops. Draw a circle. So we see that UT is the force on the wing, or the vertical component of the force on the wing. So UT, the force on the wing, M is the mass of the wing. The wing is vibrating, so therefore it encounters a frictional force V, and it's attached, but it can move up and down. So we're going to talk about a spring constant K. And this is the wall of the aircraft. So we can pick the displacement whichever way we like. So X, let us say that is the displacement in a downward direction. So we want to find the vibration. So once again, if we look at the forces, T is the force down. Then if the force is going down and the displacement is down, then the two forces are like some people in life. Any which way you're going, they're pushing in the opposite direction. So the two forces are pointing in the opposite direction. And X is this way. So we would say that UT, so that's the net force now. So let me say the net force would be UT and these two opposite forces. And these two forces always opposed. So therefore it's going to be minus VV minus KX is equal to mass of the wing times acceleration, which is the net force. Net force is always mass times acceleration. And again, can do the same thing. So MA minus B plus carry these two over this side here, plus VV plus KX is equal to U of T. So you see that we end up with the exact same equation that we started out with. Now, so what I'm saying is that the second order differential equations, we can model them and model systems using viscosity and the spring constant. So there are things that you would want to do with this differential equation. When you solve this differential equation, you might want to change k so that the solution of the differential equation will change. Meaning to say that you might want the solution to be of such that if there is a force, whatever you model the force to be, let us say that you say that the force is a constant force down. Or let us say that you say that the force is sinusoidal, for example. Whatever it is that you put for this differential equation, you might want to change k. You probably don't have a issue. You may not be able to change b, but you can also change m. And by changing these constants, then the solution of the differential equation will be different. All right. There are cases where the differential equation will come out oscillating and getting bigger and bigger and bigger. You don't want that. You don't want the k value and the m value, with the weight of the wing and the k value to be such that the is going to oscillate out of control. You're going to want that is what is called critically damped. Critically damped. For example, is when you have when you are going to take a reading with an instrument and it goes to the reading and stays there. It doesn't oscillate around the reading. A critically damped in your car is when the thing drop in the pothole and um, within one oscillation it is back level. You don't want it to be continually oscillating and so forth. So in other words, all I'm saying is that when we're looking at these differential equations and modeling systems off of them, we are looking at the solution so that we don't want we can change we are looking at so that we can change the solution. Change the mass of the wing, change the value of K. Maybe we can do something about the value of B, the friction, the viscous force, and so forth. All right. So that is here. Okay. So that is the process that we want to examine. And just the analogous circuit to this circuit here. Some people in some cultures or some people in some disciplines some people view these two things as equivalent because they end up with the same differential equation. They end up with the same second order differential equation, and the input voltage in this is equivalent to the force in this. So these two are the equivalent circuits whenever we are looking at any of our circuits. So the solution of these two basically is the same process. We just have to pick which method we're going to apply to solve the system. So they lead to the same second order differential equation. And we can use the same method that we have been using with this to the same linear differential equation. And we can use a method that we have been using on it. So so we have said that you can use the auxiliary equation and use the method of undetermined coefficients. Method of undetermined coefficients means that we have heard the term before, method of undetermined coefficients.
Yes, sir.
So in other words, if my input is a constant A, then my trial solution. Well, if it is AX plus B, then my trial solution is going to be CX plus D. If it is AX squared plus BX plus C, then my trial solution is similar. If it is um so if my input is any one of these, then to solve for the particular integral, so for the particular integral, then we know what we can try. Of course, there are some issues. If e to the kt appears in both sides, then we know that we so if it is in the solution to the homogeneous equation, so if e to the kt is in the solution to the homogeneous equation, then we don't try the same e to the kt as a try solution. We add t e to the kt instead, and so forth and so on. All right. So in other words, we have a whole class of systems that lead to second order differential equations, and our input will be all different kinds of functions, but we can use the method of undetermined coefficients to deal with it. Now, the other method that you would use to deal with a set of equations is the Laplace transform. So you can use solve the same set of equations up there using the Laplace transform. Now I know that you did it in whichever one of the maths that you know, maths 105 or however much, whichever maths course you did. And then You did have either teacher who did teach you it, signals assistant for those who did it. So I am not going to go back over the general things, but I'm just going to talk about, well, all right, can I help myself? So, tell me the definition of Laplace transform, somebody.
F of t times e to the minus st. Well, the integrator there. From 0 to infinity.
All right, so definition of Laplace transform is that if I have the derivative of a function, then that is the integral between 0 and infinity e to the minus st f prime of t dt. Replace f of t by f prime of t. But integration by parts, u dv is equal u dv is u v minus the integral of v du. So if we use this as u and this as dv, then what we are going to end up with is u, which is e to the minus st. When you integrate a derivative, we just end up with the function itself. Minus the integral of v, which is f prime of t. F of, no, dv is f prime of t, so v would be f of t. And then du, when you differentiate e to the minus st, the minus s becomes a coefficient, so therefore that's minus s e to the minus st. So therefore, that is going to be, let me just write it back for the time. E to the minus f of t, take out the minus s, become plus, and this is the same definition that we started with. So the Laplace transform of f prime of t is going to be equal. Now when you plug in infinity in an exponential decaying function, that is going to be 0, because the function is going, exponential decaying function is going down like that. So as time passes, get closer and closer to 0. So this part you're going to make that 0. And when you plug in 0 for t, that gives 1. So therefore that's going to be minus f of 0 plus s, and this now becomes the definition of the Laplace transform. So the Laplace transform of the derivative of a function is going to be equal to s f of s and so the Laplace transform for the second derivative is 0, infinity, e to the minus st, and the second derivative replaces f. So the integral here now, again, this is my u, this is my dv. This is going to be equal to u dv. So now dv is f double prime of t. So v would be f prime of t minus the integral of V, so V du there. So now this is minus, if I differentiate u, I'm going to get minus s e to the minus s. And this, when I integrate to get v, this is going to be f prime of t. Infinity at 0, infinity at 0. So once again, plug in infinity, you get 0, plug in 0, you're going to get, so this is going to be 0 minus f prime of 0. My plus, when I carry out this now, this is going to be s e to the minus s f prime t dt. But we already know what this is. This is the Laplace transform of the derivative, which we have up here already. So therefore, the Laplace transform of the second derivative is equal to, I'm going to put by the s, I put in this part of the function first. So this is going to be s, and then now I'm going to put this part here, and now e to the minus st f prime of t dt is s f of s minus f of 0, and then put this part here minus f prime of 0. So that gives me s squared f of s minus s f of 0 minus f prime of 0. So these two things we call the initial conditions of the system. You would have been given things like the Laplace transform of A. Just want to zero in on these two things. If we have an impulse function, because those things occur a lot in electrical circuits. A constant is a DC circuit, and an impulse is when there's a spike in the system. So if there's a spike in the system, then we would want to know the Laplace transform of a spike. So if a spike occurs at time t equal a, what's the Laplace transform of that? And if we have a Laplace transform of a constant, we'll just put 1 here. What's the Laplace transform of that? The rest of them we can look up. So anybody remember Laplace transform for a constant? You have t, which is a constant, which is 1. What's the Laplace transform for this?
1 over s, sir, I think.
1 over s. Let me cause this. Over the summer, I was helping one of your classmates in mechanical engineering with maths, because he said was having a horrible time. And anyone knows so much Laplace transform we do. I know. So all of these things supposed to be maybe something to them. All right, what about Laplace transform for this function? A spike at time t equal. So that is the other function that is of interest to an electrical engineer. Always what for the exam? I forget.
No, sir.
I don't remember.
I'm still taking it in, sir.
Always what for the exam at the road. Only that. Oh, So it's e to the as.
Understood, sir.
Yes, sir. We know say E to something.
Minus. All right, so DC voltage spike. So for example now, sorry, so the voltage is T minus 3. This is 0.5. Um, what is this again? I don't want to make my life difficult. Sorry, to using it as one. So now, so in other words, you have a so you have this circuit and you have a voltage spike at 3 seconds as the input to the circuit. So this is the voltage spike at 3 seconds. And them say, so what is going to happen to this to the voltages across the system as a result of that? And what would we have to increase or decrease to cause the voltage to behave through the system to behave different? All right, suppose there's a lightning strike of 5,000 volts. How will it affect the system? All right, so you remember the differential equation. Remember, I said this is L di dt. The first one is L di dt.
Yes, sir.
The second one is 1 upon C, the integral of I dt. The
Yes, sir.
third one is I times R, and that is Kirchhoff's law said that is equal to the voltage in the system. All right, so the I dt is supposed to be L di dt is when we do the Laplace transform for that is going to be L, and the derivative, as we said, is S. And the function is I, so it's L S I S. I didn't do the integral, so but let me just write it down. It's going to be 1 over S times, the integral is 1 over S, times 1 over C times I of S, and well, I times R. I times R is just I S times R. So if we are to write in terms of the Laplace transform, all right, well, let me just write down the 5t minus 3. What would we write as the Laplace transform for that?
Five.
5
5e
e to the
Three
minus
S.
3s.
All right. So now, if you take this equation, we're going to write that LSIS plus IS over SC plus IS times R is equal to 5e to the minus 3s. I'll put in the values. So L is 1, R is 1, and C. So this is going to give me L is 1, so that's SIS plus IS over S times 0.5 plus IS times 1 is equal to 5 e to the minus 3s. So I take out the IS, we're going to get S plus 1 divided by 0.5 is 2. So this gives me IS S so this is going to give me S squared plus 2 plus S. All right, so we can find the current. So we can find the current. IS is going to be equal to, carry this over here, that's 5 e to the minus 3s over S squared plus S plus 2. So we're going to ignore the e to the minus 3s, and we are going, well, this cannot be factorized. So we're going to have to do the complete the square thing. S plus half of the coefficient here, so it's a half squared. My math teacher just take 2 and minus whatever you see over here. So this minus a half squared. That's 5 over S plus half squared. Notice that I'm, sorry, 5S over, notice I'm ignoring the e to the minus 3s. I will put it in afterwards. So 2 minus a quarter is 1 3/4. 1 3/4 is 7 over 4. All right, so now we're going to go to our, let me write it this way. All right, so what we're going to do is go to our Laplace transform table and see what it looks like S over N. Can you hear me?
Yes, sir.
Yeah, yeah.
Because I'm not seeing anything that says you don't hear me at all. Okay. Thing disappear from the screen now. Okay. So the unfortunate thing about this whole entire saga that we have here is that the closest thing that we have to anything concerned with our thing, with the S in the numerator is this thing. So we just write down what we had. We had S. We had S over S. Was it plus or minus a half? Plus.
Yes, yeah.
Plus 7 over 4. And the 5 was outside. So now, here's the problem. This have a minus a in there. So therefore, we have to put a minus half in there. But if we put a minus half inside here, then we're going to have to take it back out. So we have to put a plus a half over S plus half squared plus 7 over 4. Because we have to put in the minus half for the minus a. So therefore, we put it in. So but we have to take it back out because now we're going to use this as well. So now, we are in the position now to write down our Laplace transforms. This is going to be e to the a, so this is going to be minus a half t cosine b. B is 7 over, b squared is 7 over 4, so this is going to be root 7 over 2 t. So this here, e to the minus, this part here works out. Now this other part here now is going to be b up top.
How you say that's drop in the minus half up at top again? Oh, that just drop in.
Because the thing have drop in a A inside it. So we have to drop in a A inside it. So this half. Oh, sorry, it's supposed to be plus a half. So this S minus A squared, and then you have a minus A up here. The only thing that we have that have a S up in the numerator is this. But it have a half up there. So it have the A minus A up here. So we have to put the minus A up there. So change this to a minus. So we have to put, that's the only one that we have here that we can use.
So
with this table.
Yeah, but the second equation over on the right hand side there minus that now, how that one come in?
Because we put in a half.
Not the half.
This was my original equation. S plus a half squared plus 7 over 4. So now I put in a plus half because the formula says must put in it. So therefore we have to minus it back out.
Minus it back out. Okay. Right.
So now this one here, so now is going to be minus a half, and I have to put the b up top. Now remember, so now this one here is b squared. So let me put the b up top. This half is here. I have to put the b up at the top, which is the square root of 7 over 2. But if I put the square root of 7 over 2 up there, then I have to go take it back out because it was never there in the first place. So we have to multiply. So we put the minus a half, s plus a half squared plus 7 over 4. I put a root 7 over 2 so that we can write down the answer. But there was no root 7 over 2 up here. So therefore I have to multiply by 2 over root 7. We can't step back out. Right? So these cancel out each other. So now what I'm left with is minus a half. This part here works out to e to the 8t. So therefore is e to the minus a half t sine root 7 over 2t multiplied by 2 over root 7. Yeah, I know, so we are stressing, especially at this ordinate, but bear with me. E to the minus a half t sine root 7 over 2t.
I know,
So
sir.
these two are the two solutions. Eh?
So now the class I can move to an earlier time because they must sit down at them at time of night. Great.
Gosh. It's hard for the teacher too, you know.
Make it even worse. Sir.
It works for the teacher.
Yeah, that message will make it even worse.
Teacher Ed how old, you know. Number one, and I have to remember I have all of them something we have to do. All right, so you get E that we leave out something. S minus A dot B squared. All right. So the solution now is this part here, so plus this part here, so. So let me go back to after all that rough work, we could go back. All right, we'll go back to where we were. And we're not done yet, you know. So I'm going to say I S with a little star because we're not finished yet. Is 5 thing that we just work out now, so what it is. I'll put a bracket. E to the minus a half t cosine root 7 over 2t minus, yes, 1 over root 7 sine, sorry, e to the minus a half t sine root 7 over 2t. So that is 5 e to the minus a half t cosine root 7 over 2t minus 1 over root 7 sine root 7 over 2t. But like I said, we're not finished yet. Because if you remember, we had the e to the minus 3. So if you remember their Laplace transform, or we just go to the, when we took it out, so we could have deal with and write down the answer without the t e to the minus 3 is the delay. So we'll just go back to the table and just explain the delay. If you look at this entry in the table, let's circle it. Someone, just make sure. 1 second. Yeah. If you have the e to the minus cs, this thing that can give a few problems. This function here, when you have e to the minus cs in front of the function, what it says is that you are delaying the function by t minus c. So e to the minus c, the minus c is the delay in the time. So it don't start, the time don't start at t, it starts at t minus c. So our delay is minus 3. Our delay here is minus 3. So it don't start at t equals 0. It starts at t equals 3 seconds. So what we have to do is everything that is here, our is, so that's why I put a star on it. So our is actually, somebody did right, 5 e to the minus a half. Instead of t, we're going to write t minus 3 cosine root 7 upon 2. And where is it t, we write t minus 3 minus 1 upon 7, root 7, sine root 7 over 2 t minus 3. So that is our solution here. And instead of putting u, I put that t, it start at 3. Now, that is important. We'll start dealing with the function at 3. The spike occurred at t equal 3 seconds, so everything will starting at, what this is saying is that we're starting everything at 3 seconds and dealing with it 3 seconds later. So again, what it says that this system, we can say that the maximum voltage throughout the system is going to be, well, we would have to combine these two and multiply it by 5 to find what the maximum voltage is. Or we can work out what the maximum voltage is in the system. Remember, if you remember, when you had a sine x plus b cosine x equals c to solve, and then they tell you say you must turn it into r sine r cosine x plus alpha equals c. You remember that?
To a point, sir.
Just say no. We're not kill you. Then they give you this equation to solve at some point in your life. On Earth.
It for me, I know, sir, but
Sometimes you didn't pay attention to your class, or sometimes you don't pay attention. Huh? Hmm. Anyhow, R is the amplitude. And then they tell us that R is equal to the square root of A squared plus B squared. So the amplitude is going to be the coefficient of cosine, which is 1, plus the coefficient of sine, which is 1 over root 7 squared. And this alpha, they never tell you what it was, but in electrical, alpha is the phase shift. And what phase shift is the considered another delay. So if, for example, because that's what this course name, engineering analysis. If you're going to analyze the system, then you have to be able to look, say, all right, this is what happened. How is it going to affect your system? So you have to be able to not only solve and find the solution, but you have to look at the solution to be able to say what is going on within your system. So your phase shift means, let us say that the thing was a sine wave. This is sine x. Sine x plus 60 means that there's a phase shift of 60 degrees. So instead of it starting, can't find the pen. Okay. It would start here at x equals 0, but here so. It would start x equals 0 when x is minus 60. So in other words, your function going to start 60 degrees over here and look like that. So it has shifted to the right by 60 degrees. So when you're looking at time t equals 0 over here for a system to be 0, you cannot look at time t equals 0 over here for the system to be 0 because the system has caused it to shift. So this alpha that you did work out in the maths problem is the phase shift through the system, how much the system shift the wave. All right. And whenever anything passes through a system, there's always going to be a shift. You sure, sir? When you come and you take, you're taking one way, and as you go through, you take positive or negative, your thinking change. There's a shift. Anytime anything passes through a system, there's always even a small shift. All right. So the phase shift is how much the thing has gone back or forward in the system. So now we can look at the system. We have the solution. So forget all of the whole part acrobatics where we didn't do up until we reach here. Because nobody's concerned with how we got here. But when we reach here now, so the last thing that I want us to consider for the night, all right, is that although this problem, when we started out, we said, suppose we had this system here, this inductive capacitor resistive system. Suppose there's a spike, a 5-volt spike at time t equal 3 seconds. What would happen? Well, after all of these bats, we're now in a position to say, what would happen in the system? And there are some things that we are interested in. We're interested in what would be the maximum current in the system. I is the maximum current. So now, the maximum current is going to be this 5 times the maximum value of this over here. Now I said that the maximum value of, if I have A sine x plus B cosine x, then the R is going to be A squared plus B squared. So let me just work out the magnitude R here. So clear mind out of everything what we just do. We're now looking at, this is the formula that we are getting for the current in the system. We don't care how we get it, because we can easily type the thing into MATLAB and get this same answer in 2 seconds. But what does this mean? All right, this big old long complicated thing. Well, before we have 5. Well, the first thing we know is that it starts at 3 seconds. Not never happened before 3 seconds. 3 seconds is when everything starts to happen. And we know there's an exponential, and we know that there's a trigonometric function. So therefore, we know this is the first thing that we know is going to happen in this system. We know that if you have an exponential and a trigonometric function, then it's going to look like. So the current is going to go slowly to 0 and it's going to oscillate. All right, so we know that. We know the rate at which it's going to decay, e to the minus a half t. We know the rate at which it's going to decay. But now we want to know 2 other things. We want to know the amplitude, maximum current, and we want to know if there's a phase shift. So I'm going to do it like this now to make my life easier. I'm going to say consider sine x is plus or minus. So the t minus 3, I'm going to consider root 7 over 2 t minus 3, that's x. Minus 1 over root 7 cosine x. So what is my r? My r is going to be equal to 1 squared plus 1 over root 7 squared. So that is going to be equal to 1 plus 1 over 49. So 49 over 49, so that is the r is equal to square root of 50 over 49. Square root of 49 is 7, so it's root 50 divided by 7. So that is the amplitude of that system, of the sine plus cosine part. So the maximum current. Let me see if you're not sleeping on me. So if the maximum for this part, the exponential part is 5, and the maximum of this part is root 50 over 7. What's the maximum current in this system?
Go again, sir.
You
You said the right thing, so don't say it so that that's the maximum current in the system. Eh?
They saying the maximum amplitude being 5, so when
Yeah,
be
yeah, 5, yes, sir, 5.
The maximum on this part is 5. And now we say the maximum on this part, the cosine plus sine, is root 50 over 7. So what's the maximum overall of everything?
The root 50 over 7, sir.
Times 5.
Root 50 over 7 times 5. Thank you. Equal 5 multiplied by root 50 over 7. Math class, they literally say root 50 is 25 times 2. The square root of 25 is 5, so that's 5 root over 7. So that is equal to 25 root 2 over 7. All right. And then now, if you want to find the phase shift, it's going to be what it is. You say alpha is tan inverse b over a, just like with the complex number, which is equal to tan inverse minus 1 over root 7 divided by 1. Who have a calculator can work out this way? I calculator on my phone. Update on it not working. And let me ask them to work on it. Nikai. All right, Joshua. Need a calculator. You know what me say?
Sir, minus 20.7 degrees.
Minus 20.7 degrees.
Come
So
on, they have
minus
enough.
20.7 degrees.
But you know,
Minus.
that the lecturer,
So in other words,
when calling two sons, say, you don't want a calculator. And so when you say that they want a calculator, then that me say,
You unmute me.
Kojo, yeah.
gangster.
so what mama say?
Nothing else, sir. Same, so, sir. Need the calculator, coffee.
Okay. So I was raised military style. So sorry. We did think we did soft, but we did realize
No,
late in
no,
life
sir.
is military style.
You good, sir. You good, sir.
No, no, say a gangster, sir.
So I hear in my whole age.
Attitude rough.
At the time I was thinking I was this quite like a bit well behaved and is is one of the lecturer tell me say me I had it. I did not know this my whole entire life. So a senior tell me say me I had it. And if him tell me so, I feel bad. All right. So the sorry, 1 second here. 0.7. So you know the maximum current. So you know the maximum current, and then you know the phase shift through the system, how it's going to look through the system and how it's going to vary. And then you can use the time to calculate the current at any time. So in other words, when you analyze the system, that is first of all, you have to have a model for the system. You can break it down into some simple elements. You can get a differential equation which you can solve. And when you solve it, then anything that happens, you can analyze and say, this is what is going to happen, this is what is going to happen. The maximum current going to be this now, mash up nothing, etc., etc., etc. So that is what the whole entire mathematical process is all about. Those so the calculations that we do. All right. So I missed the class on Thursday last week because for some reason we mix up Wednesday and Thursday. I think it was 2 o'clock was the class. So I whenever have a timetable. So Thursday coming, we're going to use MATLAB and solve these equations. All right. So again, the emphasis is not on solving the process of solving because as I keep on telling people, university has examined you on that and has found you competent. So with that, we are not really here to go re-examine that. So all of the things that we have been doing, we're just saying that when you're going to analyze a system with a set of differential equations, for example, we put forward some methods of proceeding or some methods of which people will proceed so you would be able to follow through or follow the act. So Thursday, we're going to look at using MATLAB and solving the same set of differential equations and see what will give in that situation. So we're not going to stress on it anymore this evening. I'll stop here. So Thursday is our MATLAB class. If you the school is supposed to have you're supposed to have access to MATLAB on your computer via the school. So just sort out that so that those of you who have MATLAB can follow. But you're supposed to be able to link with the MATLAB, put in your school ID and get onto MATLAB and get MATLAB to use. Because that's what we're going to be talking about.
Where is that, sir?
Thursday.
Sir, who do I
On the
go
website
to
or
for that
something?
information?
You're here.
You can
Talking
Who do
about
I-
the website?
It's MathWorks website and you just sign in using your
MathWorks.
school email address. Once you put in your school email address, you'll be linked to the school license.
Come
Right.
again?
What's work?
Mathworks.com.
Hold on, I'm gonna write that down.
Math.
.com. Yeah. And then you're going to sign up using your school email.
Select United States. No, there's somebody.
Yeah, select United States, continue in United States. Sign up using your school email. They'll send you a verification to your school email.
Over for the register or something? What
Yeah.
is that?
There's who
Get
was that?
MATLAB?
Yeah, no, MathWorks. Select United States website.
No, so we're just saying that you
Oh yeah, so the picture right up to the top, sir, be right beside Get MATLAB. Click there and then they would sign up through there. That yeah.
Oh, that's something there.
Yeah.
Mm.
And then you sign up using your UTech student email.
Oh,
So
okay.
create one, not no account, create one if they don't have it yet.
Oh, create one.
No, I would sign up already.
Yeah, man. But I'm just talking
Mm.
to the rest of them. So they would have create one.
Right.
Use your student email and just go through the steps through that. And then with the student email, you can download it to your PC. Because it links you to the license.
You're not supposed to have a MATLAB already. Watch your computer.
If you have a MATLAB on your computer, then fine. But like mine, we put a MATLAB on it and then we have to take it because it creates problems. If you have multi-sim, that's different.
That's different.
Yeah.
All right, so Thursday, we continue looking at we went to use MATLAB and solve some simultaneous equations, or we use MATLAB and solve those simultaneous equations. All right, so we stop in here.
All right, sir.
All right, so good night, everybody.
All right.